We will start next unit. So far we have discussed the basic control systems, that is a transfer function, and by using background reduction techniques and signal flow graphs, we have calculated the transfer function for various kind of problems. The next unit, the time response analysis. Time response analysis. So for any system, we can analyze the system in two ways. One is a time response, another one is a frequency response. There are two ways we can analyze the system. There is a time response, and other one is frequency response. First, what is a time response? That first we will see. We will highlight the time response in this unit. The response, first we will see what is the time response. The response of the control system, the response of the control system that is the output with respect to the time when the time changing a reference signal is applied. When the time changing a reference signal is applied. Right. Now the time response has two parts. Again, it has two parts. This time response. One is a transient response. Another one is a steady state response. Yes. Suppose if you draw the graph representation, this is suppose the C of t as output and t variable. So let us take, this is the system response. This we can take it as transient response. Here up to here it is steady state response. So C of t is equal to Ct of t plus Css of t. This is called natural or transient. This is called steady state. Okay, what is the transient response? We will see first. In statement wise, we have seen already in the graphical point of view. The transient response means the part of the response, So here, the part of the response of the system, when the Ct of t is becoming 0 when time becomes large, that is called a transient response. So that is the part of the response which dies becomes large. This is called transient response. That means limit t tends to infinity, Ct of t equal to 0. Next, what is steady state response? the part of the response which remains at some constant value after transient has died out, that is called a steady state response. The part of the response which remains at some constant value after transient has died out. That means when t tends to infinity, its value is almost constant. That is called a steady state response. Infinity Css of t is not equal to 0. This is called steady state response. Okay, I will continue. So the both transient and steady state response, uh, if you discuss in detail, practically no systems are transient free. Practically no systems are transient free. That is they show the transient to some extent. That is, they show transient to some extent. So no systems are transient free. So they show the transient to some extent because the presence of some capacitance, inductance are inevitable because of the presence of inertia, mass, capacitance, inductance are inevitable. With these reasons, all systems are transient free. Then the transient response, completely depends on the system nature. The steady state response completely depends upon the nature of the input and gain of the system. Similarly, the steady state response completely depends upon the nature of the input and gain of the system. The transient response of control system are examined by using standard test signals. Okay. Now, to check the system response, we can use the various standard test signals. So, where it will be useful, the importance of input signals is required. We'll see first. Suppose if you take the closed loop control system, HS, this is GS, CS, RS, yes. Now, CS by RS equal to GS by 1 plus GS into HS. Okay, right. Now, CS equal to GS by 1 plus GSHS into RS. So the response in time domain, the response in time domain, C of t equal to inverse Laplace of C of s, that equal to inverse Laplace of Gs by 1 plus Gs into Hs into Rs. Okay. Now this Gs and Hs are constants. Both are constants. Okay. Now if I change the input signal, a reference signal Rs as various standard test signals like a unit step signal, unit ramp, and unit parabola, then we'll see how the system responds behavior. First, we'll see what are the standard test signals. Number one, impulse signal. Number two, unit step signal. Number three, a unit ramp signal. Number four, unit parabola signal. So these are the various standard test signals. So we can predict the response of the system with the knowledge of input signal. So with these standard test signals, these are used to predict the response of the system. The response of the system. Yes. Now we'll see in detail one by one what are the standard test signals. Okay. So the standard test signals, first one, unit step, we'll see that is RT equal to some value as 1, that is 1, a reference signal. So its Laplace transform Rs equal to 1 by s. Next, unit ramp RT equal to T. So its signal representation is 0. So its Laplace transform Rs equal to 1 by s square. And unit parabola RT equal to T square by 2. This is 0, T. Its Laplace transform is 1 by s cube. Next, unit impulse signal delta t, its Laplace transform is 1. So out of all these standard test signals, the mostly used signal is a step signal, because for transient analysis we can examine the system for sudden change of input for short time. Also for steady state analysis we can examine at this signal t equal to infinity. So here the mostly used signal is step signal, because for transient analysis you can examine the system for sudden changes of input for short time, also for steady state analysis we can examine at t tends to infinity. T tends to infinity. The input is same for infinity time. And then the next point, since the step signal consists of infinite number of frequencies, the in frequency domain analysis, the step signal is very important. Since the step signal infinite number of frequencies, so it is mostly popularly used in frequency domain analysis. Okay, now the next topic. So we'll see the system for various order systems like a first order system and second order system, like that. So what is the system behavior for the various reference signals for a first order system, that we'll check up first. So first one, what is the response of the first order system for various reference input signals? First we will see time response of first order system. Okay, so what is the first order system? We'll see 1 by tau s, and it is a unity feedback system, Rs, Cs plus minus this is Es. Okay, right. Now to find out the transfer function Cs by Rs, we get 1 by tau s by 1 plus 1 by tau s, that equal to 1 by tau s plus 1. Okay, now Cs equal to 1 by tau s plus 1 into Rs. Now if I change the input Rs for various signals like a unit step signal, unit ramp signal, now what is the system response and steady state error we'll see first. Okay, so first case, if R of S equal to 1 by S, that is unit step signal. Okay, so now Cs equal to 1 by tau s plus 1 into Rs, that equal to 1 by tau s plus 1 into 1 by s. Okay, now to find out C of t, that is inverse Laplace of 1 by s into tau s plus 1. Okay, so if you factorize this Cs by using partial fraction, we can find out inverse Laplace transform. So this 1 by s tau s plus 1 can be written as a by s plus b by tau s plus 1. By using partial fraction method, we find the values a equal to 1 and b equal to minus tau. Now substitute the values here. C of t equal to inverse Laplace of 1 by s minus tau by tau s plus 1. So inverse Laplace of 1 by s minus tau gets cancelled here, 1 by s plus 1 by tau. So C of t equal to 1 minus e power minus t by tau. Right. Okay. Now what is the steady state error for this system? Now steady state error is equal to ESS equal to limit t tends to infinity E of t. What is E of t? So here E of t, error signal E of t equal to RT minus CT. RT is the input signal, CT is the output signal for unity feedback system. Okay. Now limit t tends to infinity, RT minus CT, that equal limit t tends to infinity. What is RT? Is 1 minus CT, 1 minus e power minus t by tau. 1 gets cancelled, you got limit t tends to infinity e power minus t by tau. Okay. Now when t tends to infinity, this become 0. Yes. Now steady state error is 0. Now the system behavior, there is no steady state error. So C of t, this is t 0. C of t will get like this. Okay. This is for unit step signal as input system behavior. Next we will see unit ramp signal as input. What is the system behavior we will see first. Next, for the same first order system, now the input signal as the unit ramp signal. We will see the response to the unit ramp signal, unit ramp input. So that is RT equal to T and R of S equal to 1 by S square. Now what is CS? CS equal to 1 by tau S plus 1 into R of S. So 1 by tau S plus 1. What is R of S? 1 by S square. Right. So this can be again partial fraction A by S plus B by S square plus C by tau S plus 1. So using partial fractions, after finding the values, A equal to minus tau and B equal to 1 and C equal to tau square. Now if you substitute the values in the CFS, that is minus tau by S plus 1 by S square plus tau square by tau S plus 1. So inverse Laplace transform C of t equal to inverse Laplace of CS, that is inverse Laplace of minus tau by S plus 1 by S square plus tau square by tau S plus 1, that equal to, you will get minus tau plus t plus tau into e power minus t by tau. Yes, that equal to t minus tau 1 minus e power minus t by tau. Okay. Now we'll find out again the steady state error. First we'll find out what is the error signal. Error signal E of t equal to RT minus C of t. What is RT? It is t, and CT, t minus tau minus tau. So t gets cancelled. You will get tau into 1 minus e power minus t by tau. This is error signal. Now steady state error ESS equal to limit t tends to infinity E of t, that equal to limit t tends to infinity E of t is tau into 1 minus e power minus t by tau. Yes, when t tends to infinity, this part will become 0, so you will get tau 1. So this is the error for this ramp input. Now if you draw the waveform, so this is a response as a C of t, and this is the RT, and this is the CT. The error is, the difference is tau. This is the steady state error for the unit ramp signal. Okay. Now, so we have discussed the first order system. Then we'll go for second order system. Okay. So the time response of second order system. Okay. So what is the transfer function? We'll see now for the second order system. This is Rs kV by S into S tau plus 1 is Cs is Rs. Okay. Plus minus. Okay. Now Cs by Rs equal to kV by tau S square plus S plus kV. We can also write in this form kV by tau S square plus 1 by tau S plus kV by tau. So this can be written in standard form for the second order system, that is omega n square divided by S square plus 2 zeta omega n S plus omega n square. So this is the standard form like P of S by Q of S. So the transfer function in the form of a rational, like a numerator polynomial and a denominator polynomial, then here this is a standard form of second order system, where zeta is the damping ratio and omega n is the undamped natural frequency, and zeta omega n equal to alpha, which is called damping factor. Yes. Okay. Actually, the time response of any system is characterized by the roots of the denominator polynomial Q of S, which in fact are the poles of the transfer function. That is, the time response of any system is characterized by the roots of the denominator polynomial Q of S, which in fact the poles of the transfer function. Yes. So this Q of S is called as a characteristic equation. Now the denominator polynomial polynomial qfs equal to 0 is called characteristic equation. Yes, so that is s square plus 2 zeta omega ns plus omega n square equal to 0. Okay. So what are the roots of this equation, and based on the zeta value, like a damping ratio, how the system, different kind of systems will get, so that we'll see now.